Hi, this is Mrs. Gorley, and this is the 10.3 lesson in BC Calculus on polar area. So first let's start with what is the area of a circle. So the area of a circle is just pi r squared. So pi area equals pi r squared. And then if I want the area of just a piece of a circle, so like a sector, so like that this is a big old circle, and you just want this section of it, then if you think about that, that is whatever that angle is right there. It's that angle out of this entire circle. It's a fraction. So that angle out of the entire circle is 2 pi radians. So we're doing this in radians. If it was in degrees, we'd say like, I don't know, 60 degrees out of 360. But it's out of radians here. We're doing radians. So if I want just the area of that, I would take my area of the circle, and to get just the sector, I would multiply by the fraction that is representing that percentage of the circle. So then the pi's cancel, and we end up with this formula for the area of the sector. 1/2 r squared times theta, times the angle there. Another way to find this area would be to slice this up into little teeny sections like this, and find the area of each individual section, and then add them up, right? Now, I don't know why you'd want to do that on a circle, because it'd be much faster to just use this formula here. But what if it was a shape that it wasn't a uniform circle like this? For instance, let's say we have a picture like this, where if I draw from the center here out to each of these places, it's a different length depending on where I'm drawing it, so that you don't have a uniform radius like you do on a circle. So now, if we have it like this, we could slice these up though, and we could say each one of these little slices is a little teeny piece of a small circle like there. So like this picture over here, like they have it. And if you get them small enough slices and you add them all up, then you get really close to what the area of the curve is, or what the area underneath this polar curve is. So it's very similar to when we had our function and then we put rectangles underneath these here. Remember when we did that? And then we said, oh, that's the area under the curve, which we said we could integrate to get that. So if we're going, say, from A to B here, if I want this area right there, then I could integrate from A to B, whatever that function is, and I would have the area under this curve right there, right? Well, it's going to be the same thing here. These are functions of r, some function of r with a theta in it. So like maybe it's something like r is equal to the sine of theta. That's not this graph, obviously, but something like that. So it's a function of theta. We do the same thing. We're still going to integrate, but we have to think about now, instead of having all these little individual slices, here we're having little individual slices that are like slices of a pie, or those little wedges. And so we have to think about what is the area of a sector. So that's where we're going to come into that 1/2 the radius squared idea. So let's look at that. The radius, some radius, and we're talking again, these are going to be different lengths for our radius each here. So some little section in there. If I want to know, first of all, how wide each one of these angles is, I would take from the beginning angle to the ending angle there. They're calling them alpha and beta. And I would just divide by the number of slices that I have. And that tells me my change in each one of those. That's your delta theta, so your change of theta, or the width of each one of the slices. Or not the width, I should say, the angle size of each one of the slices. So if we think about adding them all up, we do the area of a sector is 1/2, and then the radius squared times the angle. That's what we have there. And this is our r squared. That's the radius squared. But remember, it's a function of theta. Then we add them all up. Well, then if we take the limit of that as we go to infinity, so we make all of these little slices over here infinitely small, so they're really, really teeny, and we do it now, it becomes, we still have our half out here in front, and we have our radius squared and delta x, which is the change in, delta theta rather, which is the change in theta. So basically, that is the definition of integration right there. The limit as n goes to infinity of the sum. So that's how we get to our integration part. 1/2 the integral from alpha to beta, so that's just, these are angles now, the alpha and the beta there. It's like your beginning angle and your ending angle at just the function squared d theta. So in your book, I believe it has, instead of f of theta, it's got r squared. It's just the function. It's just r. Like in this case, you would plug in this for r in there. So this one says find the area of one petal of this curve. So it's really important that you know your graphs. If you know what your graphs look like, that's half the battle. So this particular function, I know that if I plug in, if I take some thetas and I get some r's, if I plug in 0 in here, cosine of 0 is 1, so that becomes 3. I know that this starts over here at the point 3, 0, rectangular, or 3, 0, polar point. If I plug in, say, pi halves, actually, let's plug in pi 6. That would go in nicely. So I plug in pi 6, I would have 3 cosine of 3 times pi 6. Well, that's cosine of a half, or pi halves rather, which is 0. So that gets me to this point right here in the middle there. So how did I get there, though? If you remember back from our last lesson, you had actually went like this. And if you, hopefully you've worked enough on those from the last lesson that you understand that. Remember, if it's a cosine graph and it is has an odd number in here with the theta, then it's a rose petal graph. And this would have 3 petals on it since it's an odd number, and each one of those petals has a length of 3 on it, or a radius of 3. So there's one of my petals, and I think it's just a good idea to know what these look like. It ends up going something like this, kind of an idea out there. That's not a perfect picture. They're supposed to be all the same size petals there, but you get an idea of what's happening there. You could plot points if you want to get more points on there, but really you need to know those graphs. So you need to know, like, you know, which ones are symmetrical where and how many petals and all that kind of stuff. So here's my picture of it, and it says find the area of one petal of this graph. Well, if I do the entire petal, wouldn't it just be the same thing as doing twice half a petal? So I think I'll just do half a petal here. Okay, so how do I know where I want to integrate this? I know that it's going to be the function squared, so it says 3 cosine of 3 theta squared. That's the easy part, d theta. But how do I know, oh, don't forget the half out front. How do I know what I put on my upper and lower limit here, what angles? Well, we know that this picture right here, that first angle there, that went right through that point 3, 0. That was when the angle was 0 radians. So I know that my lower part here is going to be 0, my lower limit. My upper limit, though, I have to figure out what is this angle right there. What's that angle? And my picture is not drawn the best there. It should be probably a little bit skinnier of a petal there. Okay, but I need to know what's that angle right there. And so what you do is you think about, well, how far was it to get back to 0 here? Because what I'm looking at is where was I at when I got back to 0 on the graph? Well, we already found it. Remember when we plugged in pi 6, it was 0, so my upper limit is pi 6. But how would you do that? I mean, I just randomly picked a pi 6 to plug in there. How would you know really what to plug in? Well, what you're thinking is if the point was back here at 0, right there, at the origin, then my radius there was equal to 0. So if I just take my function and I put in a 0 for r, and I solve this, then I'll figure out all the angles when when it gets back to, when the radius becomes 0. So if I divide both sides by 3, I get 0 equals cosine of 3 theta. And then we have to think, well, where is cosine equal to 0? Well, that happens at when the angle is pi halves and 3 pi halves and so on like that. So let's just take the first one, and we're going to say, well, we want this angle right here, to be pi halves. and then that'll give me the cosine of that angle is 0. So I want 3 theta to equal pi halves. So if I divide both sides by 3 or multiply by a third, I end up getting theta is equal to pi sixth. Okay, so a lot of times when they ask you to find the area, you'll notice that the other side of the where you need is back where the radius is equal to 0 again. Okay, so this is what we're plugging into our calculator, and you'll have to do that out on the main screen. You can't do it in the graphing mode. So get out on the main screen. You should end up getting 2.356, and you probably don't right now because I forgot one main thing. I only did the area of the blue section here. I wanted the entire petal, so I have to multiply this by 2 when I'm done, and then you'll get this number out here. All right, so we were talking in class today about this, and one of the students said, well, couldn't I just find the area of the entire thing, go from 0 to 2 pi? And if I go from 0 to 2 pi, wouldn't it give me the area of all 3 petals? And then I could just divide it by 3. Well, kind of. There's one small problem with that. If you go from 0 to 2 pi, you don't know it, you don't notice it on your calculator, but like if you graph this and you're going from the angle 0 to 2 pi, it actually is tracing this twice. So if you, to do any of the petals, the rose petals that have odd numbers, it only goes from actually 0 to pi. So if you went 0 to pi, that would draw that entire rose petal. The rose petal curves that have even numbers in it, like if it had like r is equal to 3 cosine of 4 theta, where you actually have to draw 8 petals, those are the ones that take 2 pi to draw. But these other rose petals, they only take pi to draw it. So you'd have the 1/2 out front, you could go 0 to pi, and you still have the r squared d theta. And then when you're done, you'd have to take 1/3 of that to get just one petal out of that. So this is 0 to pi once around, draws the entire petal, but you only want one of them, so you take 1/3. So that would also work. However, it would work if you were doing it on, say, a multiple choice part of the test. But if you're on the long answer part, they expect to see the correct angle that you got over here on your picture at pi 6. So you do have to know how to find that for the long answer parts. Okay, so here's a better picture of it there. That's a really good drawing of it. And you can see that they actually did it instead of like what we did, going from 0 to pi 6. They went from negative pi 6 to positive pi 6. So that's another way to do it, is you can just say I'm going to integrate from negative pi 6 to positive pi 6, and that's the entire petal. So you just need the 1/2 out front and the radius squared in there, whatever it was, this function right there. So our 3 cosine of 3 theta squared d theta, and that would also get you it, instead of like what we did was just take 1/2 of this size and then we doubled it there. All right, turns out that that number, that 2 point whatever it was, is actually 3 pi 4s. Not that big a deal, you know it or not. Okay, so let's see, let's move to our next one here. So the next one is find the points of intersection of these two graphs. So go ahead and graph it. See if you can do it on your own. See if you can pause the video and do it on your own, and then turn it back on and see how you did. Okay, so we have r equals 1 is just a circle with radius of 1. So we'll draw that. And then that is a limison with an inner loop, because I know it's got an inner loop because this number out front, the 1 there, is smaller than the 2. So I know it's an inner loop. I know it's symmetrical on the x-axis because it's a cosine on the end. And I know that most of it, the bigger part of the loop, is going to be over on the left side of the graph because it's a negative in the front there. So another thing that you can do when you're drawing these, I don't know if you noticed this before, was you were drawing the ones from your last lesson. But as you plot points and stuff, what it turns out is that this number in the front right here, it always ends up being on the x-axis, in this case the y-axis, because it's symmetrical across the x-axis. So I'm going to run into that y-axis at 1 and -1 there. And then they always go, all of the limicons go through 0, 0, unless it's a dimpled or convex one on there. So the ones that are like this, the ones with the inner loops, always go through 0, 0. And then it's got, if you take these two numbers, don't worry about the negative on it, just take 1 and 2, subtract them from each other, and you get 1. I know my shape is going to be over here, so I want this distance right here to be 1. That's going to be a point on it. And then if I add them together, 1 and 3, then I want my distance here from the 0 out there to be 3. Okay. And then we just draw it. It's going to have an inner loop, so it comes out like this, something like this. This isn't perfect, but it looks like that. You just have to know what your shapes look like. So I've had people say, why do I even need to know what it looks like? I mean, can't I just, if I ever wanted to find an intersection point before, all I did was set the functions equal to each other. Well, let's try it. We have r equals 1 minus 2 cosine of theta, and r equals 1. So set them equal. Okay. Whoops, I need an equal there. 1 is equal to 1 minus 2 cosine of theta. So subtracting 1, we get 0 on the left side. And then if we divide by -2, we still just have 0. And this occurs when theta is equal to pi halves and 3 pi halves. Okay, well that looks like it's getting me this point here and this point right there. So I've got pi halves for the angle and the radius of 1, and 3 pi halves for the angle and the radius of 1. That gives me 2 of the points, but I missed one. I missed that guy right there. So if you draw a picture, you'll make sure and you get all of them. You won't have this problem where you missed one. So the other point there that we missed by doing this is the point pi. If you go out pi, and then the radius of 1. So that's my third point. Or I could have said this instead. I could have said I'm going to go the 0 direction, so looking to the 0 angle, and then go -1. These are the same point, right? Either one. In fact, there's an infinite number of ways to write every point. So, but I wrote it like this just because there is another algebraic way to get this. If you know the radius is 1, well, you could also say, if I want that circle right there, I could also say r equals -1, because instead of just drawing it out this direction, I would draw it back that direction. I mean, it doesn't make any difference. So I could also say r equals -1 and solve this system here, or these two equations, set them equal to each other. And when you do that, subtract 1 from both sides, and then divide by -2, you say, where is cosine of theta equal to 1? Well, that happens at 0. That's when theta is equal to 0. So that is when r is -1, theta was 0. That's that point right there. That's that other point. But the fact of the matter is, if they say use algebra to find it, you would at least have to show this much. But if it's like multiple choice or something like that, you don't even need to show any algebra. If you drew them and you know what it looks like, you'd be fine. You could get those 3 points of intersection right from that. Okay, so always draw your graph. It can be very, very helpful. Here's their picture of it. Same thing, and you notice how they wrote their points. See that third point? They did it as the 0, -1, or -1, comma 0, which is the 0 angle. But if you had written it as 1, comma pi, it would be also correct. You just have to realize those are the same thing. All right, so the area between two curves. So now we've got these two graphs, and we have to find the area between them. So the first thing you want to do is graph them. So again, go ahead and pause the video, turn it back on when you're done, and see how you did with your graphing. Okay, so I have -6 cosine of theta. Well, that is a circle of with a diameter of 6, and it's, is it crooked? There we go. Circle with a diameter of 6, and it's on the negative side of the axis over here. So it looks like it's probably going to be about right here. I'm not very good at drawing these free-handed. There's our circle, diameter 6. And it's cosine, so it's symmetrical over that x-axis. Okay, and then we want this one. See how our numbers match this time? So that's the limison that's a cardioid, looks like a heart. And it's symmetrical on the x-axis again. It's a negative in front of the cosine, so again it's to the left here. And this time we've got this number in the front here was a 2, so that means I'm going to go out on my y-axis, if you call it y-axis on here. I guess it's the, if you're in polar, you're thinking up on the pi halves and the 3 pi halves angles. I'm going to go out to 2. Then if I add 2 and 2, I get 4, so I know going out this direction, I'm going to end up out there at -4, and if I subtract those two, I'm going to get 0. I'm going to end up right there. So this is my cardioid. Something like this kind of a guy. Okay? Now we want the area common in the that's bounded by the 2. So we want all of this area in here. Now I am going to go to the next graph because it's a much better picture. Okay, so there's the exact same thing that we just had. Okay, now they've already got this colored in, and this pink and the blue area. That's the total area that we want. Plus, we want the same thing down below. So we actually want the pink and the blue area that are colored in there doubled to get the entire area that's enclosed within both of those. So why is there a pink and a blue area? Well, think about it. I'm going to try to make this a little bigger so you can see this really good. If I'm making those little slices from the origin out here, when I'm in this little part here, see how each one of those slices, as it gets out to the end, it's touching the circle out here on the end. Those are on the circle. So from this section, from right here to right here, where this dotted line is there, I want to have the circle as my R. Okay, so inside there, from whatever this angle is, which is straight up, isn't straight up pi halves. Straight up is pi halves. And then this angle, which it already says on this picture, is 2 pi thirds, but we'll show you how you would get that. And then the R in here is the circle, which was our -6 cosine of theta squared d theta. That's that part. But then I have to add to that the pink part. So if you look at the pink part, whenever you start drawing the lines in here to slice it up into little sections, it's landing out here on the cardioid. So this time, on this integral, I want to go from the 2 pi thirds here out to pi angle, going all the way to the left there. So 2 pi thirds out to pi. But this time I want the cardioid is the R in there. So that one was 2 minus 2 cosine of theta squared d theta. Now don't forget, this is the one thing that everybody forgets, is you don't forget you have a half out in front of each one. And technically, I'm doubling it now to go to 2, so I'm going to just be multiplying both of those by 2 to get the other part. But you do have to show, even though that 2 times a half ends up equaling 1, you have to show that because it's part of the setup. Okay, if you don't show it, you will miss some points on the test. Okay, so there's the whole thing, and when you put it in your calculator, you end up getting 15.708. Now, the one thing we kind of skipped was how did we get this 2 pi thirds angle? And I would have back here, and I should have done this first, sorry, but back here, I would notice that I need to know where those intersect each other because of that, because I've got these two different sections here going on. So I would just set these equal to each other and solve for that. So I've got my -6 cosine of theta has to equal the 2 minus 2 cosine of theta. If we add 2 cosine of theta to both sides, we end up with -4 cosine of theta is equal to 2. Divide by -4. We get cosine of theta is equal to -1/2. And then we go, where does that occur? Oh, on the unit circle. Let's see, that occurs when theta is equal to 2 pi thirds and 4 pi thirds. So you can see on the picture, there was our 2 pi thirds, and here was our 4 pi thirds. Okay? So if you wanted to think about that, another way that we could have done this over here was if we wanted the entire thing, we could have done 2 plus, or not 2, sorry, a half. 1/2 times the integral from our first one here was pi halves straight up to 2 pi thirds of the circle. That's our 6 there. And then you could have said, oh, I'm going to double that, so times 2, because that takes into this other piece down here. And then you could have added to that 1/2 the integral, and you could have gone all the way from 2 pi thirds to 4 pi thirds if you wanted, instead of doubling like that, and then do the cardioid on that. So there's lots of different ways to do it. It doesn't really matter which way you do it. You just have to make sure you get to that same answer, the 15.708, the approximate answer, I guess. Okay? All right. So drawing the graphs, super important. Whenever they have 2 graphs and they want the area between them, most of the time you're going to have to figure out where they intersect, like that. So keep that in mind as you do the homework. So this one, find the area between the loops of this function. So I'm going to multiply this out just so I can get it in the form I'm used to. It is 2 plus 4 sine of theta. Now I can see, oh, it's got an inner loop. It's a limison with an inner loop. This one is symmetrical over the y-axis because it's got a sign in it, and it's a positive in the middle there, so I know that most of it's going to be above the x-axis here, above the horizontal axis. So if I add 2 and 4, I get 6, so I know that this point is on there. I know 0, 0 is on there where the loops cross, and I know that 2 minus 4 is 2, so I know the inner loop comes out to here. This number in the front is a 2, so I know these are going to be 2s. I just know this because I've done so many of them. If you play around with it, you get really good at them. Okay, and then we connect it. So maybe if I go this way, I can do it better. Something like that. Not perfect, but it's okay. All right, so we want this area on the inside here, right? All of this area. But I don't want that loop there. I want the area between the loops. The problem is if I do the area, say, from this spot over to maybe straight up, something like that, if I do this area here, it'll get that inner loop part in there too. So you're going to have to then subtract out this inner loop part. So let's go down to get a better graph here. This is a better picture of it so we can see what we're doing on there. So it's kind of like I have 2 functions here. Where are the functions crossing? Well, they're crossing, the inner loop and the outer loop are intersecting right here where r equals 0, right? Where the radius is 0, that's at the origin. So I'm just going to put in a 0 for r and solve this. So if we subtract 2 and divide by 4, we end up getting negative 1/2. So where is sine negative 1/2? Well, sine is negative 1/2 at, once around the unit circle, at 7 pi sixths and 11 pi sixths. So this would be one, they probably give this to you on a calculator portion. You could graph a bunch of points if it wasn't by calculator. You could go by hand. You could go theta and r, and you go, okay, when I plug in a 0, I get a 2. Well, that's that point there. And I'm just plugging them into this. And when I plug in a pi halves, I get a 6. So that gets me up here. So it must have gone like this to get up there. And then when I plug in a pi, I get a 2. Well, that's coming back down this other side like that. And then when I plug in 3 pi halves, I get a negative 2. So it's going, 3 pi halves is looking this direction, but then it's going negative, so it's going back up to this point there. So that's looping all the way around like that. And then I get back to when I plug in 2 pi, I get back to 0. So that was its path it took on there. Now I know that at 7 pi 6 and 11 pi 6, it hit, whoops, this was supposed to say 2 on it, sorry. Let me change that. I'm back to 2 there, not 0. At 7 pi 6 and 11 pi 6, I am at 0 radius. So these could be on there too. They fit in between here. As we get right here, let me get a different color. Right here is 7 pi 6. Can you see that's kind of like where this is coming in here? This coming in right there and at 7 pi 6 at that angle. And then it's coming out at 11 pi 6. Like that, 7 pi 6, 11 pi 6. So if I want, let's just do this by half of it. Let's say I want this half right there. Well, then a straight up is pi halves. So I could integrate from pi halves to the first that comes in here is at 7 pi 6. And I have the half out front, and then I'm going to double it, so I'll put the 2 right now so I don't forget it. And then the function is the 2 plus 4 sine of theta squared, d theta. Okay, that gives me the whole thing, but then remember I got to take out this part in here because it's too much. So that's going from 7 pi 6 and then straight up and down here at 3 pi halves, right? Because to get to that point right there, it was 3 pi halves. That's this point right there. So now we'll subtract from that 1/2 the integral from 7 pi 6 to 3 pi halves. And then that's doubled, remember, so times 2, and then that function again. Okay. So you do have to do these. You can't just say, oh, I'm just going to do the whole thing from 0 to 2 pi and see what it is, because what it'll do is give you all of this area here. If you go from 0 to 2 pi, it'll tell you all of that. And then it'll add this. So you'll be getting this inner loop twice if you do that. So this is the only way to do it like that. And technically, too, if you actually watch it trace and stuff like that, this 7 pi 6 to 3 pi halves is actually the right side of this circle. It's just the way it looks weird when you go to draw it, but it doesn't really matter because they're the same size, so it doesn't matter. You could have done it as 3 pi halves to 11 pi 6 on the limits there, and it would be the same thing, same exact thing. Just like I could have done this one from negative pi 6 up to pi halves kind of thing. Okay, that turns out to be 33.351 approximately there. So you can double check your work on that, make sure you're getting that. And I believe that is it for that problem. One thing too on a calculator, you might want to try putting this into a calculator here and just seeing how it works for you. If I go into my R, so I'm in polar mode and I'm on radians, so make sure it's polar mode and radians, and then go in and type in R equals 2 plus 4 sine of theta, and then go into your window. And in your window, change the theta step, that's how often it's going to mark your angles and stuff, to pi 12. So I think it defaults to pi 24ths. But I like pi 12ths in there because it still gives you a pretty good picture, a nice smooth picture. The smaller the steps you get, the more precise of a graph you're going to get. But if you make it pi 12ths, then you can go in and you can hit trace in there, and once you're on trace, you can type in like 0, and it'll put you right on the beginning point. For this one, it'll be right there because you're typing in the angle of 0, and it'll start you where it starts, and then you can just hit your arrow key, and as you go over, each time you hit the arrow key, you know you're moving pi 12, so you can kind of count what's going on. It's kind of nice. It helps a little bit. It's not a huge deal if you do that or not. Another thing is you want to change on the windows, you can change your X-min and your X-max. They do them by the polar, not the polar, but the rectangular. So you got to be thinking, well, I got to get up here to see at least the 6. I want, so you can adjust them in here in the Y min and Y max too, so you can see it better. Another trick when you're doing these on a calculator is you just hit graph, but then you hit zoom and then square. I think it's number 5 on my calculator anywhere. If you go zoom and then you square it up, it will give you it'll actually square it up so it doesn't like distort it, make it oblong so you can't tell what's going on. And then you can zoom in on things you want or whatever. So those are just some helpful hints on it. But it's super, super, super important that you know your graphs. So if you don't know your graphs yet, you got to go back and make sure you know at least the circles with the sines and cosines and R equals. And you got to know your limicons, especially the inner loop ones like this one and the cardioid ones. You got to know the rose petals where you've got an odd number in there with theta and an even number, and like which ones are symmetrical where. All of those kind of things, you really, really, really need to practice those. It'll make this polar section so much easier for you. Okay, I believe that's it for our lesson. Yeah, let me know if you have any questions, and see you next time.